How's it going, ladies and gentlemen? Mr. Donahue here once again. This time we're going to take a look at molecules and molecular compounds. So our objectives will be to predict when covalent compounds will form and describe the difference between molecular and empirical formulas. So atoms, compounds, and molecules. So what do these terms mean? Well, an atom is a single nucleus and its electrons. So maybe this is an atom of lithium, right? So we got a nucleus and the electrons on the outside. That's one thing. It's the basic building block, right? So what's a compound? Well, a compound is when two atoms of different elements bond together chemically in definite proportions. So like, let's say, for example, here we have lithium ions and fluoride ions, and they're bonding together. This is an example of a compound because it's bonded together different elements. Whereas a molecule is when you have two or more atoms bound together as a single unit. So here I have an example of like H2O, right? So this is a molecule of H2O, of water. Here's where it gets a little confusing because they're not describing necessarily opposite things. There are molecules that aren't compounds, and there's compounds that aren't molecules. All right, so let's take a look at an example. So in this example, this is definitely a compound because it's made of two elements and they're bonded together chemically. So that makes it a compound. Check. Is it a molecule? No, this is not a molecule. Well, let's take a look at what makes a molecule. Here's a molecule. It's two atoms bonded together. So here I have an example. It's oxygen. It's O2. It's two oxygen atoms that are physically and distinctly bound to each other. So those two oxygen atoms are always going to be stuck to each other. All right, so this is not a compound because it's just one element, but it is a molecule. And then we have what's a lot of things, ones that are both. This is an example of a compound and a molecule, right? I have H2O. So I have different elements bonded together, and they are distinctly bonded to each other. These two hydrogens are stuck to that oxygen, and that oxygen is stuck to these specific two hydrogens. Whereas in this example of lithium fluoride, oh, well, this should be lithium, right? This fluorine or fluoride ion can be attracted to that lithium ion, but it could also be attracted equally so to that one. So there's no distinct molecules. All right, so hopefully that helps clarify some things. All right, so what's meant by diatomic molecules? Well, let's break it down. Di means two, and atomic means atoms. So if we're talking about diatomic molecules, we're talking about molecules that are made of two atoms. So many elements are found naturally as diatomic molecules. And the ones specifically are the Brinkelhoffs. Sometimes you'll hear them called because it's bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Whenever you're talking about their elemental form, it's as a diatomic molecule. So we got hydrogen, it's always going to be H2. Nitrogen, oxygen, fluorine, chlorine, and bromine are always showing up in pairs. Molecular formulas. So the atoms in a molecule are bound to each other by bonds. The molecular formulas let you know how many of each element are in a single molecule via the subscript. So for example, H2O, what it is actually going on is there's two hydrogens bonded to an oxygen. So that's going to be its molecular formula. It's telling you there's two hydrogens, and if there's no number written there, there's a 1 and 1 oxygen. How do you know it's a 1? Because if it was a 0, they wouldn't bother putting it, right? You could put all the elements that exist with a 0 next to them. Why are you going to bother doing that? Right? Oh. So yeah, so the 2 there is telling you that there's two hydrogens. What's kind of weird is that the subscript comes after the element. So you go hydrogen, how many? There's 2. And then oxygen, how many? If there's no number there, it's a 1. And they make a single molecule. C2H6, as an example, it's telling us we have 2 carbons and 6 hydrogens all bonded together to make a single molecule. And what that molecule is actually going to look like, if you're curious, is a lot like this. The hydrogens are bonded to the carbons are bonded to the hydrogens and each other. Special note, most molecular substances will contain only nonmetals, right? Hydrogen, it's a nonmetal, even though it's on the left side of the periodic table. It's a weirdo, but it's a nonmetal. Carbon, also a nonmetal. So when they bond together, they're sharing electrons, right? These two dots right here are representing electrons that both of those atoms are sharing. Whose are they? They're both of theirs. They're sharing. Molecular and empirical formulas. So the molecular formula represents precisely how many of each element are in a molecule. Empirical formulas are different. They give the relative number of atoms in a molecule in the smallest whole number ratio, right? So empirical means it's from data, right? So experimentally, we can get the ratio of each element, but not necessarily what each molecule is, right? So if I had a C2H6, well, I don't know what's actually making up that molecule, but what I can do is I can break it apart and see what parts I get. So now it's like, all right, I broke up and I see that I got 2 carbons and I got 6 hydrogens, but I don't really know how they're bonded. And plus, I don't even know, did I break apart one molecule or did I break apart multiple molecules? I don't know. So the empirical formula is going to show you the ratio. Well, if, I broke that apart, it's like for every 1 carbon, I have 3 hydrogen. And that's what I'm getting experimentally. I can figure out the ratio between those, but I don't know, was this 1 molecule? Was it 2 molecules? Was it even 3 molecules? I don't know. But I can tell you the ratio between those elements that make it up. So if you have the molecular formula, it's really easy to get the empirical formula. You just simplify the ratio to become the smallest whole number possible, right? So sometimes the molecular formula is also the empirical formula. Sometimes it's the same thing. So if I had C2H6, I go, what does 2 and 6 have in common? I can divide both of those by 2, and I end up with CH3. If I had H2O, well, what does 2 and 1 have in common? 1, it's already simplified as much as I can simplify it, so its molecular formula is also its empirical formula. That can happen. All right, if I had C6H12O6, again, it's the same process. Let me think, what does 6, 12, and 6 have in common? Well, they have 6. So I go, all right, let me divide each thing by 6 and see what I get. I have CH2O. Does anybody want to take a guess why they call these things carbohydrates? Does anybody want to take a guess? Why would they call that if that's this empirical formula, carbohydrates? Anyway, in order to go from empirical to molecular, you also need to know the molecular mass, which you would get experimentally, doing a whole different thing. So that's a story for another video. All right, so formulas. How do we represent these molecules? We have structural formulas. It's, molecular formulas simply tell you what is in the molecule. It doesn't tell you how it's all put together. Structural formulas will show you how they are connected. They're showing you the structure. So for example, H2O. Well, this is the molecular formula, but what's its structural formula? Its structural formula is showing you the bonding. How do those 2 hydrogens and oxygen, how do they bond together to make a molecule? C2H4 is again telling me I got 2 carbons and 4 hydrogen, but nothing about how they're connected. So here, this molecule actually has a double bond. And now I can see its structure with its structural formula. We'll get into how you figure out what the structural formula is in another video. N2, all right, I got 2 nitrogens, and how are they bonded together? This one, there's a triple bond. Again, I'm not talking about how to get the structural formula, just what they are and what it shows. Other visualizations. There's a perspective drawing. And what's nice about perspective drawings is they're showing you kind of the 3 dimensions, but you can draw this out relatively easy on a piece of paper, right? The wedge here is showing you that it's coming out towards you, and the dashes are showing you that it goes behind. Whereas the straight lines are telling you it's right on the plane of the paper that you wrote it on. The ball and stick model start to show you like the 3 dimensions, and the space filling is really showing you like, all right, the actual size and geometry of those atoms as they take up space in 3D, right? In the ball and stick, we have no sense of scale in them for how big is that atom. You just see how they're connected in their bond angles. So summarize, can you explain what is meant by an atom, a compound, a molecule, and when molecular compounds will form? Do you know what's meant by diatomic molecule? And can you convert from molecular to empirical formulas? Can you describe how molecules are visualized? Structural formulas, perspective drawings, ball and stick model, space filling model. And then we'll close parentheses. Hopefully you can. If not, I failed you once again. And I'll have to see you in class. Goodbye.